Hello and welcome back to Paleocast. My name is Dave Marshall and this is the first part of episode 114 on horseshoe crabs with Dr Russell Bicknell of the University of New England, Australia. As many of you may know, I mind to profess the fondness of giant underwater arthropods once or twice in the past, and so this episode is A, something I may have had a vested interest in recording, and B, is something that I forcefully contribute my own knowledge to the extent that we spilled over our recording time and I had to split the episode into two parts. This first part deals with the horseshoe crabs, their anatomy and their ecology, so what they look like and how they live, with sizable interjections from me about the closely related eurypterids or sea scorpions. And the second part, which will be released soon, will be looking at the fossil record of the horseshoe crabs and discussing their conservation and what it means to be, in inverted commas, a living fossil. This interview is based on Russell's recently published Atlas of Fossil Horseshoe Crabs, and the link to that open access paper will be made available on our website. And whilst there, you can also take a look at some of the pictures of horseshoe crabs we're discussing in this episode. Finally, we have a couple of projects for you to check out. First is our Paleocast Gaming Network, which is now available across all social media channels, and it's where professional paleontologists and me play, review, and critique computer games for your enjoyment. Second is the newly released Paleo Nerds podcast, so find them at paleonerds.com and anywhere where you can download podcasts. It's great to be able to welcome them into the family of paleo podcasts, of which there are now a huge number for you to choose from, so we do appreciate you being here with us today. I hope you enjoy this episode. Hi Russell, thank you so much for being with us today.
Cool. It's great to be here, I must admit.
Good. So as with everyone that we have on the show, we want to know about you. We want to know how you got to where you are today. What was your route into paleontology?
Well, I was a 4-year-old boy at one time, and my father showed me a trilobite. And he said, Russell, this is an animal that is no longer alive today and was alive a very, very long time ago. And I thought that was just really cool. And then he basically said that people who study these things, study animals that are no longer alive, are called paleontologists. So as opposed to being enamored with dinosaurs, I actually started with arthropods.
And you never stopped?
Well, yeah, I suppose that is kind of an accurate summary. I did geology and German, actually, in undergraduate, with the goal of being a paleontologist. And my master's, I looked at things called foraminifera, specifically the things floating around in the ocean, so planktic foraminifera, which aren't arthropods. But my PhD was exclusively exploring aspects of arthropod evolution, and it's what I'm doing to this day.
I didn't know you did forams. Did I? Did I know that?
I hope not. It's part of my history that I'm okay just letting fall into the annals of time to be forgotten.
Yeah, one day I'll be able to say the same and leave forums behind, but unfortunately it's my job. Right. But speaking about jobs and leaving them behind, what would you do if you weren't a paleontologist?
I really don't know. I think I've always wanted to be a paleontologist. Well, I did actually want to be a steam train engineer at one point. Not that that's really a job that exists. My grandfather was part of the New Zealand Railways, and I think that's where that came from. But yeah, I can't think of a job that doesn't involve me looking at fossils, to be honest.
Hey, steam train engineer, that's absolutely fine. I'm only like stone's throw away from where the first railway was.
That's
in Manchester to Liverpool.
That's so cool.
Stevenson's rocket? That would have
Yeah,
been trundling by my window at 4 miles an hour.
that's too awesome. Ah,
Yeah, it's pretty cool. Heart of the Industrial Revolution here.
yeah, of course.
Anyway, that's a little aside. So your first love was your trilobites and arthropods, but how did you begin working on horseshoe crabs in particular?
So my PhD had 3 assigned topics, uh, one of which involved using the modern day American horseshoe crab to effectively model how we think extinct organisms that look similar to horseshoe crabs would have eaten things. And as a sort of preamble to that particular piece of research, uh, I ended up doing a 3-dimensional micro CT and CT based atlas of the American horseshoe crab. And sort of I suppose, parallel with this, a colleague of mine, Steve Pates, he and I had started working together at this point, and he had a bunch of uh, malformed fossil horseshoe crabs. And he said, "Do you want to work on these?" And that got me really interested. So I then contacted a colleague of mine in the States, Mark Botten, who's one of the key researchers on the American horseshoe crab, and asked him if he had any photos of any weird looking horseshoe crabs, and he had a bunch. And sort of from that paper, a whole bunch of interest for myself, I suppose, blossomed. In particular, I had wondered if anyone would be stupid enough to put all of the different horseshoe crab species into one place. And it was that particular thought process that sort of led me down the path of a bunch of taxonomy that I've been doing for, oh gosh, 3 years now, I think. Yeah.
Best 3 years of your life.
Definitely the most alcohol fueled.
But like, that's putting them all in one place. You mean in a research paper to say, like, here's every single horseshoe crab that has ever been that we know about?
Exactly. So basically, I had wondered, I mean, these sorts of atlases of organisms are pretty rare in the modern day. It was obviously a very big thing at the turn of the 20th century. If you were looking into a particular group of animals, you would try and present as much information as was known. But of course, in the digital age, there's so much information out there that very few people are insane enough to try and put it all in one place if you're studying something. So in this case, yeah, it was me asking, how much do we know? What has been published? And if we put it all together, what does it all look like?
Well, let's come back and have a look at the fossil horseshoe crabs as a whole later on. Let's first give everyone an introduction to the group and get to understand a bit of their biology, their ecology, and all of that. So, they're called horseshoe crabs. Why are they called horseshoe crabs, and what is in a name, really?
So I'll start with the first part. The horseshoe basically comes from their shape. So the modern day horseshoe crabs have a sort of a half moon shaped head or prosomal section, cephalothorax, if you're part of another group of thought. And the original work on them effectively was what aligned them with that name. Um, the crab part is unfortunate. They're not crabs at all, although traditional taxonomic work had compared them to crustaceans. And the similarities, and there are some similarities, had been the reason why they were grouped with crustaceans. We know now that they are actually more closely related to spiders and scorpions than they are to crabs. But the name, which is an unfortunate misnomer, has basically become just part of the modern day vernacular regarding the group.
Yeah, it's interesting that they were thought of as crabs. Like so many things. If it's in the sea, it's a crustacean, and that seems to be like 1800s and earlier. That line of thought. Like you'll find the research paper, and it might be on, in my instance, Eurypterid sea scorpions, and it'll be included in fossil crustaceans of wherever, and it's so hard to find them because you're looking for fossil chelicerates, which are the spiders, scorpions, horseshoe crabs, and all of that. But back in the day, they didn't realize that they're actually related to arachnids, really.
Yeah, exactly.
So we've got our horseshoe-shaped head. What does the rest of them look like?
Well, the modern day horseshoe crabs, their, I suppose, butt end kind of looks a little bit like a misshapen hexagon with lots and lots of spikes. And then beyond that, they have a very long and sword-like telson or tail part. Depending on where you are in the fossil record, they have some variation on that body design, but that's generally what defines a horseshoe crab.
And something I hear a lot as well is that telson, that tail spine, venomous in any way?
No, it's not. I did read a report a couple of years ago that outlined that someone had an infection after standing on the telson, but it wasn't the tail itself. It was exposure to some other chemical in the seawater that resulted in that infection. They're actually really harmless animals.
Yeah, on holiday when I was about 12 or something in Florida, I was on a jet ski, and as one does on a jet ski, fell off into the lovely coastal waters around Florida and came face to face with an upside down horseshoe crab, and promptly freaked out because I had no idea what it was. An English person, like little teenage me, not even teenage, child me in America, with this horrendous giant alien looking arthropod just floating around next to my face. And I was so scared. I did not know what it was. And it was covered in spines everywhere. And I know now that it was upside down and those were its legs. What are those spines on its legs?
Well, they've got an array, a battery of spines, I suppose, is a fairly decent description on different parts of the legs. The most interesting are the spines that are proximal to the body, so closest to the body. These spines are what we call gnathabasic spines. That's just fancy language for spiky bits that function effectively like teeth. So these spines on the closest parts of their legs to the body are used effectively to crush up shell and also to shred soft, squishy stuff during feeding.
Is that unique to the horseshoe crabs, or are there any other animals living or extinct that have those kinds of spines?
So the sorts of spines that we see on horseshoe crabs are observed sort of in these things called copepods, and they're weird crustaceans. But the best comparison would be in fossil things. You mentioned earlier the sea scorpions, the Eurypterids. They have very, very similar sorts of spines on their legs. I would argue they're probably a lot more developed in the sea scorpions than they are actually in modern day horseshoe crabs.
So we got gnathabases in horseshoe crabs, we've got them in Eurypterids, and we've got them in copepods, you said?
Yeah.
And also trilobites. Are all of these animals closely related? Are some more so than others? What's the horseshoe crab's closest relative?
In the ones that you just mentioned, the closest relative would probably be the sea scorpions. Um, but in terms of, I suppose, the general look of them, trilobites are quite often compared to horseshoe crabs because they do really have a overall generally similar look, although trilobites of course have that really segmented body, whereas horseshoe crabs don't really have that segmentation, at least in the adult stage.
So, understanding that they're not closely related to trilobites, could the behavior and lifestyle, so the ecology of horseshoe crabs, tell us about any other large arthropods from the fossil record? And that's a question from Terry, one of our listeners.
So I would say that horseshoe crabs are a really good analog for a lot of those weird arthropods, specifically marine arthropods in the fossil record. They give us a really good insight into the feeding mechanics of things like trilobites, of various arthropods from the iconic Burgess Shale that had these gnathabasic spines. Horseshoe crabs also give us some insight into the potential limitations on effectively what you can do with a body of that sort of segmentation. They have the ability to sort of enroll or roll up, so they sort of slot themselves together. And that can give us an idea of potentially how effective trilobites, which we know for a fact could enroll, were able to. Beyond that, the study of horseshoe crabs has been really informative in understanding the limitations of the aforementioned sea scorpions and their ability to eat things, potentially the limitations on what they could eat and how they would have functioned as predators within the Paleozoic ecosystems.
One of our listeners, Jim, commented that they have so many eyes. Does each set provide different types of information to the horseshoe crab?
Yes. So when we're talking about eyes and horseshoe crabs, the I suppose vertebrate notion of what an eye is isn't necessarily the best way of looking at it. They have these lateral compound eyes, so fairly large, multi-lensed eyes on the sides of their prosoma, and they're pretty much only used for finding mates. They really don't have very good seeing capability. In fact, the resolution is incredibly low. Beyond that, though, they have an array of, I suppose, features that would be considered eyes that give the horseshoe crab information about light and about, in that regard, what's around them, whether or not there's something above them, or whether or not effectively they're close to a light source.
Yeah, so the optics is something I was doing my PhD on, and before I had to quit it because I had no money. That's the life of a self-funding PhD student. But horseshoe crabs have the most amazing visual systems, not in terms of resolution. They're blind as a bat, really. If you think that an eye of a horseshoe crab produces an image not as we see it, but kind of as a mosaic. It works like pixels on a screen, except where my screen is 1920 by 1080 pixels, a horseshoe crab is going to be, oh God, how many lenses do they have? Let's say...
Yeah. Not many?
Yeah. Is not many. So something like a dragonfly, something like an Anomalocaris had 20,000, was it? I think. Oh, I can't remember. Where's Pato when you need him?
Probably hanging out with his pugs. I think it's between 16 and 20,000 was the number. I can't remember off the top of my head, though.
Yeah. So that's a lot. But horseshoe crabs, not very many. So they can't see in a great resolution, but they can do some absolutely amazing things with the light collection. So if we have any photographers here, then you know that with lenses, the size of the aperture depends on how much light you get in. And horseshoe crabs have amazingly large lenses and they can collect so much light. And then, so you've got a lens that's adapted for light collection as opposed to resolution. There's a trade off between the two. So a dragonfly has absolutely like thousands of lenses, but each one of them is incredibly tiny. So you can get a really high resolution image, but you can't get an image that is very bright relative to horseshoe crabs. So they wouldn't be able to fly around at night because it'd be absolute darkness. Horseshoe crabs, on the other hand, have these lenses that are so well adapted to collecting light that they can actually see really well in the night. And there's been studies done looking at how horseshoe crabs find mates in the daytime and in the nighttime. And they looked at, they made some concrete horseshoe crabs and put them in the sea and saw like how many male horseshoe crabs attached to the back of these concrete ones thinking they were a mate. And there was no difference between night and day, even though the light had dropped by, I think it's like a factor of 1,000,000 or something like that. I don't know exactly what it is. But they had a look at the physiology of the eyes, and there's, even though the eye is completely static, the lens can't move, it's just a solid crystal. But all of the cells and all of the pigments around it, they can change. So in the daytime, it moves pigments into its eye so that it stops light leaking between the lenses and stuff. And then in the nighttime, it retreats all of that pigment. And also, it can increase the sensitivity of its lens. So imagine on your camera for photographers, if you increase the ISO, which is the sensitivity of your camera, then you can artificially increase the brightness. Horseshoe crabs can do that. And they can increase the sensitivity of their lens, of their eyes, by a factor of 1,000,000 times brighter. They can make their images, and that perfectly corresponds with the reduction of light at night. So that means that horseshoe crabs effectively see just as well in the daytime as they do in the nighttime. So they can't actually see nighttime at all. Mind blown when I found that out.
Yeah. Well, I just learned something. That is freaking awesome. Wow.
Yeah.
So, if you don't mind my asking, that knowledge that you've amassed there that's associated with a project that you have had on the go for a while, because that is an incredible outline.
Well, horseshoe crabs are a kind of a model organism for visual systems in arthropods because they've got such giant eyes in terms of like actual size. So even though like dragonflies have relatively bigger eyes compared to their body, horseshoe crabs have the biggest eye in absolute terms. And loads of horrific experiments where they like cut open the head and stick in probes and measure the electrical impulses from the eye and stuff like that. So a whole load of arthropod optic work has been done on horseshoe crabs, and so they're incredibly well studied, their optics. And yeah, so all of that just came from one study. And it's not something that I found out, but it's something that's incredibly well studied in the field of arthropod optics, which is a field that many people do.
That is just some really cool stuff. I mean, I have touched briefly on horseshoe crab eyes, but that particular piece of work was more interested in the fossil record, or effectively the lack thereof, in, I suppose, stem horseshoe crabs. I haven't had the opportunity to explore in depth the literature around their eyes, but that is absolutely mind blowing. So thank you for that. And yeah, wow.
Hey, it's fine. I can talk about this stuff all day. Hey, let's do an interview with. If you want an interview with Dave Marshall about arthropod optics and what you can learn about the fossil record and what things can see, leave a comment, give us a thumbs up. We probably won't do it in the future. But then, you know that Eurypterids share the same kind of optical system as the horseshoe crabs, because there are fossil Eurypterids, these absolute giant 6-foot pterygotids. There's some in Canada, I think, that have the lenses preserved, because the lenses are made out of... Dave, come on. The lenses are made out of cuticle, and if you get that cuticle preserved, I think I said before they were made out of calcium. No, I didn't. I said they were made out of a crystal. They're not made out of crystal. They're made out of cuticle. So the lens is made out of cuticle, and if you get a fossil that's well enough preserved, cuticle can sometimes preserve in the fossil record. And there are Eurypterid lenses known from the fossil record, and they are the same lenses that horseshoe crabs have. So we have the best studied arthropod visual system in horseshoe crabs, and we can directly infer stuff that we know about their optics to the Eurypterids because they have the same lenses. And so it's so easy to look at the visual ecology of horseshoe crabs and just transplant that into Eurypterids and say, if we know that the horseshoe crab can do this and that, and this is how it sees, we look at Eurypterids and say, okay, so if we increase the size of the horseshoe crab eye, increase the number of lenses by however many, or decrease them, or increase the diameter of each lens or decrease it, then we can start to think about how Eurypterids were able to see. And this is a huge emerging field in the study of sea scorpions, and there's been lots of research done on what they can see, a lot of which I disagree with what's been published, and that was going to be the whole point of my PhD. And so there's this one giant pterygotid sea scorpion called Cuteramus, and it had these giant eyes. Oh my god, they were so big, and they had the biggest lenses. They were like plates. And some research that was done just said, like, look, come on, these couldn't see anything because they had such giant lenses, and so few of them that any image would have been so rubbish. It would have not been a very good predator, really. And either that or it hunted at night. And yeah, probably hunted at night, but it would have been absolutely perfectly adapted to have seen anything passing in front of it at night. And resolution of your eyes is only an important factor when you consider either the distance away that your prey is or the size of your prey. Okay, so if you've got a poor resolution image, if I just used my phone and took a picture outside, there may be a fly flying past at maybe 10, 20 meters. It's going to be hard to get that image of a fly on my phone camera. Okay, but if it was a car passing at that distance, okay, then we'd be able to see it. And equally, if that fly was closer to my phone, say maybe 30 centimeters away, then I'd be able to actually get the image of that. But equally, if a car was passing 30 centimeters away, it's not going to be pretty hard. You're going to get that picture of a car, yeah? So this sea scorpion would have had absolutely perfect vision for spotting either something close to it or something large, especially at night. And so I figured, hey, this is probably an ambush predator of large prey at night. So you look at all the possible ways in which something could see something, and then you can start to build a picture of its ecology up. And that's all thanks to these horseshoe crabs that we get to learn about these other giant arthropods in the fossil record and what they were able to do.
Yeah, no.
Again, mind blown.
Yeah, that's yeah. So a slight tangent, but if you are of the opinion, and I do agree actually, that the larger sea scorpion species were predators, what do you think they were predators of? Out of curiosity.
That I haven't really come up with something. We'd have to have a look at the size of the chelicerae and think that you would have to have something. Well, they would have to be able to grab something that is approximately the same size as their claws. I mean, there were plenty of fish going around. My presumption is that they were some of those. There has been some weak evidence that there have been predation of pterygotids on some armored fish. There are head plates of fish that have sequential holes in the top of their heads, and that has been presumed from a sea scorpion grasping it and piercing it along. So I don't exactly know, but equally I don't care, because I know that they were eating something successfully with what they had. And until you get some direct evidence, then you could speculate anything. It could be something that we just don't have fossilized in the fossil record. There could be giant squidgy worms. Don't know.
No, that's a very good point. I'm just now imagining sea scorpions going after giant squishy worms. That's quite an amazing image.
And that was the conclusion of Laub and Tolleton, that they couldn't possibly be predators except for of vegetation or soft-bodied prey.
Right. Okay.
But you got to think that they had spine, like they had these giant claws. Imagine a crab, sort of like that, but they had claws of death. Those were their teeth at the front of these sea scorpions. They had to be catching something that needed to be held. It needed to be caught in these spines and pinned down. They didn't want to let it go. If it was simply just catching and cutting, then the shape and the size of the claws would be different. So imagine a crab claw, that's for crushing. It's got lots of blunt spines. The Eurypterids had, some of them had like bluntish spines, but they're all pretty pointy. And to the extreme that Acutaramus had a very particular shape claw that had a giant spear in the middle of it. I mean, that was, if you have a look at an Inuit fishing spear, it's exactly the same as that. And that the Inuit fishing spear is designed to hit a fish, and then the spines of the spear like wrap around it, and the main piercing bit of the spear pierces it at the same time. So it's an impaling and catching device, and the Acutaramus teeth do effectively the same function. I think, with no evidence at all. This is just speculation.
I'm inclined to agree. It just makes sense, right? In terms of function, why would you put energy into developing such an effective and almost extreme morphology to only use it to eat squishy worms? It just doesn't make much sense to me either.
Yeah, it's crazy. Some of the things that people come up with for the ecology of Eurypterids. There was a study recently that said that they use their tail spine, effectively the same tail spine that horseshoe crabs have, as a weapon, as a cutting tool, effectively a sword that they swung laterally, like from side to side, hacking at whatever it caught in in its teeth, and you're just like, where has this come from? Like, they would have a very specific shape and function, and if you have these giant claws filled with teeth, they are intrinsically linked to how it eats. It's not just an accessory to its other weapons, in inverted commas. Yeah. The field of paleoecology is an incredibly important thing, because we've got to keep in mind that although we study dead animals, those animals were once alive, and we know all about their morphology and their anatomy from what we can see, but each one of those was alive. It was a functioning, successful animal that had a huge amount of time on the earth where it was successful, where whatever it was doing was absolutely wonderful and worked for it at that time. And so in that light, you got to view everything as having a specific purpose and reason and use, or at least it didn't detract from anything.
No, I absolutely have to agree with you on that. I mean, while evolution doesn't necessarily have a particular direction, things arise because of selective pressures, and then they tend to survive for however long because they were able to, or they simply and quite rapidly go extinct because they just didn't do a good enough job. So I totally agree with you. These sea scorpions in particular, with their array of, I would agree, their weaponry, their toolkit, one might say, were undoubtedly, I would say, effective, very effective predators, of what, of course, we don't necessarily know. But yeah, you're right. They were effective for quite a long period of time.
So getting back onto script, obviously you guys would never have worked out that was all unscripted. Terry wants to know how long horseshoe crabs live and how often do they produce young? And does that reproductive cycle make them more resilient or at risk?
All right, three-part question. Let's go. How long do they live? I don't know. And I don't know if anyone actually knows how long they live. They have what we call a terminal molt. So horseshoe crabs are arthropods. They have an exoskeleton, and they effectively, to get bigger, they need to shed their exoskeleton. They molt the exoskeleton, and then they grow. They have effectively a point at which they stop doing that. While the amount of time that it takes to get to that terminal molt, which I believe is 14 years, that's very well documented. The amount of time that a horseshoe crab can live after that, I don't know if that's actually been documented. I would hazard a guess in saying that it would probably take the lion's share of a career to actually determine how long a horseshoe crab lived. Partly because you probably have to keep it in a lab, and they get pretty big. But even then, in lab conditions, the reality is that isn't actually natural. And when you do capture and release, you're not necessarily always going to get the same individual back. So I don't know. I would say quite a while, though. How often do they reproduce? On a yearly basis. I can tell you that one. So they have effectively a yearly. Am I allowed to use the word orgy? I think that's probably the best description here.
Sure.
Yeah, cool. Basically, it's
A mass spawning.
They on a yearly basis, they'll come up onto shore or close to shore. And they'll have effectively a mass gathering of these animals, and they'll do the reproduction. that mode of life, which is effectively external fertilization, not like us vertebrates, does mean that they can produce a lot of eggs, and a lot of eggs can be inseminated. But there is the trade-off in that the eggs themselves are then just left, and they are hopefully able to survive through into maturity to let the cycle continue. In the process between making of the eggs and the actual becoming an adult, horseshoe crab babies are prey to a lot of different things. It's probably about the only period in their life where they're actually able to be consumed with ease, because they don't have that really hard exoskeleton that the adults have. And so it's that initial period, that early development, in which they can potentially struggle to get through. So in that regard, the means with which they reproduce can cause problems, but the frequency doesn't have anything to do with it at all.
How do they know when this mass spawning is going on? They don't get an invite on Facebook or whatever. How do they all manage to congregate in the same place at the same time?
I mean, you're assuming that horseshoe crabs haven't already invented Facebook. Come on, mate. You know?
That is a presumption.
Yeah, come on. Well, if we work off the most parsimonious...
Prosoma book.
Exactly. So if we work on the assumption that they don't have a mass Facebook invite, I am not 100% sure. So one of the listeners may correct me in what I'm about to say, but I believe it's basically built into their biology. It's effectively not necessarily a learned behavior, but it's part of their hardwiring. I would also wager, because it happens in summer, that there is effectively a transition in the water temperature that would, I suppose, flick a biological switch that would tell them, okay, hey, it's time to go and do my yearly attempt at making sure my species doesn't go extinct.
Isn't it to do with the moon?
No.
No?
Well, okay, there are a lot of papers that have...
And tides?
Not a lot of papers, but there are papers that have suggested that there is a strong correlation between the timing of horseshoe crabs mass spawning and the waxing or waning of the moon. A colleague of mine, Wynne Watson, who I think is now retired actually, who spent the lion's share of his career looking at the brains of horseshoe crab and also nudibranchs, because why not? When I visited him some years ago, we actually got onto this topic, and it's of his opinion that it's not related to the changing of the timing of the moon. Tides, though, there is, I'd say, probably more logic behind that. I myself don't have a lot of experience in the actual reproductive biology of horseshoe crabs, because my focus has been mostly on using them as tools to understand biomechanics of extinct things and then understanding the fossil groups. So in that regard, what I may have just said may be taken with a grain of salt, shall we say.
So as a whole, this reproductive strategy of being an aquatic animal but laying your eggs on land, what's that all about? What are the advantages of that? Because all I see for horseshoe crabs is a ridiculous effort for all of these aquatic animals to all meet up at the same place, mate, lay your eggs on land, which is not even where you live, and then just leave them for everything to eat and just hope that a few of them survive. So what's the benefit of doing that?
So I suppose the point to make there is it's not like they crawl up into the streets of New York and do do their business. I would love to see that. I admit, sounds like a horror film. The eggs are laid themselves, of course, on the beach, and it's fairly close to the water. So there's still tidal action, which effectively allows the eggs to be moved into the water, and then they're able to be kept within within the water during that early development. As to why they do that, honestly, I don't know. It really, to me, it doesn't make a lot of sense either. I would have thought that reproducing within the ocean would make a lot more sense, given that they are marine organisms. It may come down to effectively reproducing in an environment where when water isn't going to just get rid of the sperm immediately. So you put the eggs in a place where they aren't going to be swept out, and then during external fertilization, those eggs can actually be fertilized because basically they haven't just been swept away by an oncoming wave, if that makes any sense.
And I think you've got to think of it in terms of when this behavior first started. So if they've been reproducing like this for hundreds of millions of years, the environments that they were laying eggs in should we go back as far as the Paleozoic, in the Mesozoic, Jurassic, Cretaceous, it's very different to what we have now. And so it was probably, I think, going to be a lot safer to lay your eggs on land than it would have been to have laid them in the marine environment, at least then. Even if it's not so now, it's still a successful enough strategy that the horseshoe crabs are still alive. It still works for them. So I think they're kind of stuck with it.
Yeah, I mean, once again, coming back to that concept of evolution not necessarily having a direction, but when something works, it sticks. I think that's exactly the case. They've been doing it for, if the work on the Xiphosura is correct, 480 million years. And it's a reproductive process that has kept them, ticking over for quite a long period of time. So it really, at this point, doesn't make any sense to change.
Sure. So let's go back to 480 million years, you said. Was that their first appearance in the fossil record, yes? Paleocast was brought to you by Dave Marshall and Liz Martin Silverstone, with contributions from Tom Fletcher, Vish Venkat, and Elsa Pancharoli. Music was composed by Patrick Kendall Smith. Paleocast was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on funding from you, the listeners. So, if you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programs, and follow us across social media platforms to get all the latest news. Finally, if you enjoy our podcast, then please explore all of our video content on YouTube and follow our other projects, the Virtual Natural History Museum and the Paleocast Gaming Network.